Hey students, welcome back. This is part 2 of the electrical nature of neurons, and what we're going to talk about now are action potentials. So we're just going to pick up right where we left off. So as you can see on this very first slide, you've got a red line here. This is the action potential graph. This is something that we are going to come back to time and again, just so that I can kind of show you what's going on with the membrane potential in our neurons. Okay. So remember that an action potential occurs when multiple local or graded potentials summate or add together at the axon hillock of the neuron. But also just bear in mind that if the sum of their membrane potentials at that moment don't reach threshold, then an action potential will not occur. And it'll just disappear. It'll go away. We're not going to get propagation of an action potential down the axon at all. Okay, so we have a number of phases of an action potential that you need to know. The first one is resting. That's kind of like a salty banana. And next is threshold. Remember, that's a maybe. Then we have depolarization, repolarization, hyperpolarization, and recovery. And during recovery, we have something called a refractory period where the sodium-potassium pump is working to reestablish the resting membrane potential. And then we go back to resting, back to our salty banana. A couple of reminders. Remember that when a neuron is at rest, it's not really stable. Like, I don't want you to equate those two words together. And remember also that if something is polarized, it means that there's a separation of charge. And when we're talking about the neuron, when the neuron is at rest, we have more positive ions on the outside, more negativity on the inside. And when we depolarize, when we take away that separation, you're going to have positive things moving into the cell. During repolarization, you have positive things moving out of the cell, and that's going to cause the membrane potential to become negative again. So we are re-separating the charges. And then we have hyperpolarization. Remember that prefix hyper means excessive. Now we have excessive separation of charge. Okay. So the membrane potential of a neuron that is that is conducting an impulse is going to change as the action potential proceeds. So remember that a neuron at the hillock is going to start at rest, and the resting membrane potential is negative 70 millivolts, which means that the inside of the cell is negatively charged, and that the difference in the potential or in the charge is 70 millivolts between the outside and the inside. And so our channels are like ligand gated, which is going to, which means a neurotransmitter is going to come bind to a channel on the surface of our neuron's dendrite. And if it's excitatory, it's going to allow some sodium to flow in. And if enough sodium flows in at that point to become more positive, then it's going to cause other areas of the cell membrane to become more positive as well. And that's going to cause voltage gated channels to open. And now we're going to get a lot of sodium coming into the cell. All of these local potentials are going to travel from our dendrites through the cell body and then down to the place where the axon sprouts off the cell body of the neuron. It's a place that's called the axon hillock. And once all of these little local potentials go there, then they're going to add together and combine. Okay, at the axon hillock, if once combined, all of the excitatory graded potentials and all of the inhibitory graded potentials get there and they all add up, and they reach threshold, which is a negative 55 millivolts, then bam, you're going to get an action potential that travels down the length of that axon. And it's all or nothing. So if they don't reach negative 55, like if you have more inhibitory graded potentials than excitatory graded potentials, for example, you're not going to reach threshold. And so therefore you're not going to get an action potential moving down that axon. So we're just going to talk about the excitatory ones, though, because I want you to know the parts of the action potential. So when threshold is released at the axon hillock, that means that voltage-gated channels at the hillock are going to open and sodium rushes in. And that's going to make the membrane potential more positive because you're taking positive things from the outside of the cell and putting them into the cell, which is normally negative, but now it's going to become more positive. And that's going to keep on happening until the membrane potential reaches about positive 30 millivolts. This is called depolarization. You are reversing the separation. You are depolarizing. Polarizing means it's separating. Depolarization means you're taking away the separation. At the same time, our potassium channels are also stimulated to open, but they are very slow to respond. So they're stimulated at the same time as sodium channels are, but they open really, really slowly. I kind of like to think about the sodium channels as the front door of your house and the potassium channels as like the automatic garage door of your house. Like if you want to open the door to your house, you just open it and it's open and you can walk in. But if you press the button on your remote and your garage door goes up, it doesn't just like fly open. You've got to wait. Like you can't pull your car in until you've totally gotten the door open. So you have to wait. That's what our potassium channels are doing. So even though they're starting to like open, they're not opening enough to allow for the movement of potassium through them yet. So they're slow to respond. Okay. Now, once our membrane potential reaches positive 30, now our potassium channels are going to open. Our potassium channels are going to open, and potassium is going to rush out. So remember, potassium is positive. If we have positive things leaving the cell, that's going to make the membrane potential, the inside of the cell, more negative. This is repolarization. We are reseparating the charges around the cell membrane of this cell. And now our resting membrane potential is going to become more negative. You can see on the voltmeter that we have an arrow there showing you the negative slope of the reading. And it's moving back towards zero. Once the membrane potential reaches positive 30, our sodium channels, they close up. And just like the door, just like your front door, they are going to close very, very quickly. And now you've got whatever sodium is inside of the cell, it's trapped there for a while, folks. But now our potassium channels are open and you've got potassium rushing out of the cell. Now, because the potassium channels just open slowly, they are also going to close slowly. And so while the potassium is running or flowing, I guess, out of the cell, now your channels are going to start to close, but they're closing slowly, 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 slowly. So our potassium ions are going to have a lot more time to escape from the cell and get into the extracellular fluid. In fact, so much potassium is leaving the inside of the cell that we get hyperpolarization. We get excessive separation of charge. And our membrane potential is going to dip below resting, below negative 70 millivolts, all the way down to about negative 80 or negative 90 millivolts, again, depending on the source that you're looking at. And so this is what we are looking at here. We are looking at our line. You can see that when threshold is reached, we have our stimulus gated sodium channels are open. And once we reach, and remember that threshold, like that's happening at the axon hillock. Then, once our membrane potential reaches negative 55, now our voltage-gated sodium ion channels are going to open. You're going to get sodium channels flowing in until you get up to about positive 30 millivolts. At that point, your sodium channels are going to close and your potassium channels are now fully open. Remember that they were stimulated to open at threshold, but they open very slowly. But now by the time we reach positive 30, they're open all the way. So now our potassium ions are going to rush out of the cell. They continue rushing out through the purple part of the graph. And they even are going to have more time to rush out because, again, those potassium ion channels are going to close very, 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 very slowly. So those potassium ions have a lot more time to leave the cell. And so the lowest dip in our red line. That's at negative 80 millivolts. That's hyperpolarization. But now if you look at the graph, you can see that we have a little bit of a positive curve happening there. So we're going to talk about what's happening there next. All right, our sodium-potassium pump is now going to work. We have our sodium ion channels closed, our potassium ion channels are closed, and the pump is using ATP to push sodium and potassium against their gradients. It's pushing 3 ions of sodium out and pulling 2 potassiums in at a time, at the same time. And in doing so, it's going to return the resting membrane potential back to negative 70 so that we have a polarized cell. We have we have a positive charge on the outside and we have a negative charge on the inside. Okay, so during this time, we have a refractory period. So while the sodium potassium pump is working, the local area is going to resist restimulation. So you're not going to be able to get an action potential kind of piling up on one that's already happening. Right when the sodium ion channels are open, that's an absolute refractory period. You're not going to get another action potential at all during that gold area of our graph. In the relative refractive period, when we have repolarization and hyperpolarization, you could get another action potential, but the stimulus would have to be very, very strong. And what I mean by a very strong stimulus is that you would have to have stimuli reaching that neuron at a very high frequency. We're not talking about remember, it's got to be at negative 55 in order to open the channels. That can't change. Even if it's stronger, it just has to reach negative 55. It's not going to make the magnitude of our action potential graph any bigger. But if you have bam, 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 it's kind of like, someone is poking their finger at that neuron, trying to get it to respond, then you could, during the relative refractive period, get another action potential to occur. Okay, so our action potentials are going to occur in one chunk of our membrane and then to another one and then to another one. It's going to be a chain reaction because as the local area depolarizes, that's going to cause the next segment to depolarize and that causes the next one to happen. I just want to mention that our action potentials, because of this, are never going to travel backwards, from the axon terminal on backward towards the dendrite, because the previous section is in a refractory period. And I wanted to also mention something called saltatory conduction. You already learned that some axons are wrapped in something called a myelin sheath. And there are little gaps in that myelin sheath. And what that's going to do is it's going to allow for an action potential to occur in a gap, and then it spreads extremely quickly through the insulated area, the area that's covered with a myelin sheath, over to the next gap. And then it's going to spread very quickly through that insulated area. So basically what saltatory conduction is it's kind of like a jumping. In Latin, the saltore, I think is the root, but it means to dance or to jump or to leap. And so the action potential leaps from gap to gap to gap, not necessarily having to go through all of the areas that are insulated. All right, this is a preview for what comes up next, everybody. Thank you so much for listening. And if you have any gaps in your notes, just go ahead and replay the video. That's the beauty of it. Until next time, bye-bye.